Okay, so let's go ahead and take a look at differentiability and continuity. So the derivative of f at c is defined by this limit definition. And there's a couple of different limit definitions that we've looked at. But this one allows us to look a little bit better about, whether or not there's a cusp or a corner where you have a non-differentiable point. So if the left side limit is equal to the right side limit, then the derivative actually exists. But if these are not equal, then the derivative does not exist. So there's a couple of pictures. This is a corner. Here's a cusp and a vertical tangent and a vertical asymptote, where you have a all non-continuous points. And at those points, so at A, in all of those examples, it's not differentiable at those values. Okay, and it should be A, not C here. Okay. All right, so limit definition of the derivative. We've talked about this before. And in normal circumstances, you would have been given like an f of x is equal to something, and then you would have had to find the derivative using the long way. College Board actually wants you to be able to take something like example 1 and extract out that this is the definition of the derivative. So when you see this limit, this looks like the definition of the derivative. I look at my last term, ignoring that, provided that it's a subtraction, I only look at this cosine. So my f of x is actually cosine of x. My f prime would be negative sine of x, and then I take my pi. So f prime of pi is negative sine of pi, which is 0. So that's the definition of the derivative. So overall, this limit is equal to 0. If this was a plus sign instead of a minus sign, then your f of x would have been negative cosine of x, and then everything would have been switched by a positive or a negative. Okay, but it was subtraction, and it's defined here as subtraction, so my f of x is just my cosine of x. I take that pi, that number that's there, and I replace it with x. Okay, we understand derivative of any constant, so any number is equal to 0. Power rule is the second one. You can add and subtract derivatives. So if I'm looking at example 2, my f prime of x is equal to 6x squared, and my f prime of 1 is equal to 6 times 1 squared, which is 6, and f prime of 0 is 6 times 0 squared, which is equal to 0. So that's my answer for all 3 of them. Looking at example 3, derivative again, power rule, 3x squared minus 10. Product and quotient rule, we've done before. Second times the derivative of the first plus the first times the derivative of the second is product rule. And then this is like your low d high minus high d low over low squared. So, and that's quotient rule. So example 4 is product rule. So y prime is equal to x to the 4th plus 8x minus 1 times 3 plus 3x minus 5 times 4x cubed plus 8. And so I can distribute this out. So y prime is 3x to the 4th plus 24x minus 3. And then, it's not equals. And then plus, I can FOIL out my second term, which is 12x to the 4th minus 20x cubed plus 24x minus 40. And if you don't want to FOIL and you want to use the box, you're more than welcome to. Then I combine my like terms, so 15x to the fourth minus 20x cubed plus 48x and minus 43. Okay. Example 5 is quotient rule. So f prime is the denominator times the derivative of the numerator, which is 1, minus the numerator times the derivative of the denominator, which is 1, all over the denominator squared. So f prime of x, 2x minus 10, plus 10, minus 2x plus 1, because I distribute my negative sign to both terms, over x plus 5, the quantity squared. So f prime of x, my 2x and my negative 2x cancel out, so I'm left with 11 in the numerator, and x plus 5, the quantity squared, in my denominator. Okay. Next thing is chain rule. Chain rule is used when I have like f of g of x and taking the derivative of f of g of x. So you have to identify an inside and an outside function. So when I look at this first example, my inside function is 3x minus 5. My outside function is the 10th power. So my y prime is equal to 10, 3x minus 5 to the 9th, and then times the derivative of the inside, which is 3. So y prime is 30, 3x minus 5 to the 9th. And then here, example 7 is a product rule, and within the product rule is chain rule. So first let's write our f of x, rewrite it again. This is 25 minus x squared to the 1/2 power. So my derivative is f prime of x is equal to the second, which is 25 minus x squared to the 1/2, times the derivative of 5x, which is 5, plus 5x, times the derivative of my 25 minus x squared to the 1/2, so bring the 1/2 down, 25 minus x squared to the negative 1/2, times by negative 2x. So then my f prime of x is 5, 25 minus x squared to the 1/2, minus 5x squared, 25 minus x squared to the negative 1/2. And this, remember, this is like our factoring like we did in our summer work. F prime of x, pull out my negative exponent, so 25 minus x squared to the negative 1/2. I could also pull out a 5 if I wanted to. And then I'm left with 25 minus x squared to the first power and minus x squared. So I get f prime of x is equal to 5, 25 minus x squared to the negative 1/2. And then I get 25 minus 2x squared. So f prime of x is equal to 5, 25 minus 2x squared. And then this to the negative 1/2 power goes to the denominator. So 25 minus x squared. And that's my answer. My next one, my inside function, is my quotient, and my outside function is my third power. So y prime is 3, 2x minus 1 over x squared, and then low d high minus high d low over low squared. So I get y prime 3, 2x minus 1 squared over x to the fourth, because I can distribute my squared to my numerator and my denominator. 2x squared minus 4x squared plus 2x over x to the fourth. So y prime is 2x minus 1 squared. My numerator here becomes negative 2x squared plus 2x, and all divided by x to the 8th power. I have a common 2 in my second set of parentheses, so y prime is equal to, and I can factor out a negative 2x or a positive 2x. I'll factor out a negative 2x, so negative 6x, 2x minus 1, the quantity squared, x minus 1, all over x to the 8th power. So, remember your trig function derivatives. So, derivative of sine is cosine, derivative of cosine negative sine, derivative of tangent is secant squared, derivative of cosecant is negative cosecant cotangent, derivative of secant is secant tangent, and derivative of cotangent is negative cosecant squared. So, example 9, my y prime, 12x plus the derivative of secant x is secant tangent. So that's my solution. Example 10 has chain rule, so y prime, derivative of sine is cosine of 2x, times the derivative of cosine, which is negative sine of 2x, and then times the derivative of 2x, which is just 2. So I actually had 2 little chains there. So my outermost function is my sine, my next inside function is my cosine, and then finally my other inside function is 2x. Inverse trig, so all of my arc sines, my arc cosines, and my arc tangents. Arc tangent is the same thing as tangent inverse. So my derivative of tangent inverse is 1 over 1 plus x squared. But it is root x, so this is root x, the quantity squared. Because that is inside of the arc tangent, this is a chain rule. So multiply by 1/2 x to the negative 1/2. So f prime of x is 1 over 1 plus x times 1 over 2 root x. So f prime of x is 1 over 2 root x and 1 plus x. Okay, and then arc cosine. So y prime is equal to negative 1 divided by my 1 minus my x, which is 1 over x, the quantity squared, and then times by my derivative of 1 over x. So 1 over x is the same thing as x to the negative first power, so this is negative x to the negative second power. So y prime, negative 1, square root 1 minus 1 over x, the quantity squared, times 1 over negative 1 over x squared. So y prime is a positive 1 this time. X squared root 1 minus 1 over x squared. Since it's not a multiple choice, I'm totally okay with you guys leaving it like this. Okay. Remember your derivatives for e. A to the x, where a is a number, ln, and then log. So 13, y prime, e to the 3x times the derivative of 3x, which is 3, plus, now this e cubed is just a number, so this is 5e cubed times the derivative of x, which is just 1, and then plus the derivative of e cubed, which again is just going to be 0. So my y prime is 3e to the 3x plus 5e cubed. 14 is product rules. So y prime, e to the x times the derivative of x, which is 1, plus x times the derivative of e to the x, which is just itself, minus e to the x times the derivative of x squared, which is 2x, plus x squared times the derivative of e to the x, which is e to the x. So y prime, e to the x, plus x e to the x, minus 2x e to the x, minus x squared e to the x. So you have a common e to the x, 1 plus x minus 2x minus x squared. So y prime e to the x, 1 minus x squared. 15. This is just a number, so this follows the a to the x rule. So y prime is a to the x times ln of your a, and then times your chain rule, which is the derivative of sine, which is positive cosine of x. Y prime for 16, e to the x cubed, because the derivative of e to the x is e to the x, times the derivative of the exponent, which is your chain rule, so 3x squared. So y prime is 3x squared, e to the x cubed. Again, you have a chain rule for 17. Y prime, bring down the 5, ln of x to the 4th power, times the derivative of ln of x, which is 1 over x. So y prime, 5 over x, ln of x, the quantity to the 4th. Okay, so 17. Y prime, 1 over x squared plus 2x minus 3, because the derivative of ln is 1 over the inside, times the derivative of the inside, which is 2x plus 2. And then the derivative of ln of 5 is just a constant, so that actually ends up being 0. So y prime, 2 times x plus 1 divided by x squared plus 2x minus 3. Example 19, y prime. This first part is a product rule. So ln of x times the derivative of 2x, which is 2, plus 2x times the derivative of ln of x, which is 1 over x, and then plus the derivative of x, which is just 1. So y prime, 2 ln of x, plus 2, plus 1. So y prime is 2 ln of x plus 3. Example 20, y prime is 1 divided by the x, which is 2x plus 1, times the ln of 5, which is your base, and then you have to multiply by the derivative of the inside, so the derivative of 2x plus 1, which is just 2. So y prime, 2 divided by 2x plus 1, and ln of 5. Slope of the tangent line, we've done before. Derivative, plug in the point. Slope of the normal line is perpendicular to the tangent line, which means opposite reciprocal, which means flip the fraction, flip the sign. Okay, so your slope of your tangent line being equal to 0 means that there's a horizontal tangent, and if it was undefined, you would get a vertical tangent. Okay. If the slope of the tangent line is 0, then the slope of the normal line is undefined. And the slope of the tangent line is undefined, then the slope of the normal line is 0. So let's look at 21. Write the equation of the tangent line for this curve. Nobody likes e, so we'll do this one. Okay? Derivative of e is itself. So y prime of 1 is e to the first power, which is just e. Y of 1 is also e to the first power, which is also e. So the equation of the tangent line, y minus e is equal to e times x minus 1. So then we could talk about implicit differentiation. Remember, implicit differentiation means that anytime we take the derivative of y, we write dy dx. And remember, implicit comes from chain rule. So if I want to find dy dx for example 22, take the derivative of y, which is 2y dy dx. Derivative of 7y is negative 7 dy dx. Derivative of x squared is 2x. Derivative of negative 4x is negative 4. and then that's equal to 0. And then what we're going to try to do is isolate my dy dx. So 2y dy dx minus 7 dy dx is equal to negative 2x plus 4. Factor out a dy dx on the left-hand side. So 2y minus 7, negative 2x plus 4. So dy dx is equal to negative 2x plus 4 divided by 2y minus 7. Do the exact same thing. For example, 23, 3x squared plus 3y squared dy dx. On the right-hand side is a product rule. I can factor the x out. So I have y times the derivative of x plus x times the derivative of y. And remember, the derivative of y is 1 dy dx. So I get 3x squared plus 3y squared dy dx is equal to 6y plus 6x dy dx. Move my dy dx's to the left. Move everybody else that doesn't have dy dx to the right. So I get 3y squared dy dx minus 6x dy dx is equal to negative 3x squared plus 6y. Factor out a dy dx. So I'm left with 3y squared minus 6x is equal to negative 3x squared plus 6y. So dy dx, negative 3x squared plus 6y divided by positive 3y squared minus 6x. They all have a common 3, numerator and denominator. So I have 3 negative x squared plus 2y, 3y squared minus 2x. The 3's cancel out, so dy dx is negative x squared plus 2y divided by y squared minus 2x. Okay. Write the equation of the tangent to the curve at that coordinate point. So first take the derivative implicitly. So 2x plus 2y dy dx. Derivative of 19 is 0. Derivative of 2x is just 2. Plus the derivative of 12y, which is 12. Dy dx. So 2y dy dx minus 12 dy dx is equal to 2 minus 2x dy dx. 2y minus 12 is equal to 2 minus 2x. So dy dx is 2 minus 2x divided by 2y minus 12. They have a common 2 in the numerator and denominator, so 1 minus x and 2 times y minus 6. So dy dx is 1 minus x divided by y minus 6. I can then plug in my coordinate point of 4, 3. So I get 1 minus 4 and 3 minus 6, which is negative 3 over negative 3, which is 1. So then my equation of my tangent line, y minus 3 is equal to 1 times x minus 4. You could leave it like that. You could distribute, or I'm sorry, move the 3 to the right-hand side, so y is equal to x minus 1. Okay, 25. Graph of is of the original function below. Find the approximate value of f prime of 3. So we can use the mean value theorem. F prime of 3 is approximately equal to f of b minus f of a over b minus a. So I look where 3 is. Here's where 3 is. So I'm going to go from 2 to 4. So f prime of 3 is equal to f of 4 minus f of 2 over 4 minus 2. So f prime of 3 is equal to 5 minus 2 over 4 minus 2. So f prime of 3 is approximately, these should all be approximately, equal to 3 halves. Okay? So, 26. Let f be a continuous and differentiable function. Selected values of f are shown below. Find the approximate value of f prime at x is equal to 1. So, I look where x equals 1, and I want to sandwich between 0 and 2. By the mean value theorem, f prime of 1 is approximately equal to f of 2 minus f of 0 over 2 minus 0. So f prime of 1 is approximately 2.08 minus 1 over 2 minus 0. So f prime of 1 is approximately 0.49. Okay, and now this notation here means I'm taking the derivative of the inverse function. Inverse function, back from a previous class, to find an inverse function, you take x and y and you flip them, and then you solve your equation back for y. So in this case, I would have had x is equal to y cubed plus 2y minus 10. And then I would have needed to try to get y by itself. I can't actually get y by itself because I have a y cubed and a 2y. And this doesn't factor into a perfect square where I can isolate my y easily. So, because I need to find this derivative of the inverse, I do my first step of finding the inverse. Because I find the inverse function, so this is technically the inverse function, the x equals y cubed plus 2y minus 10. I can then find the derivative of the inverse without actually isolating my my y, because I have implicit differentiation. So that means everywhere I see y, I can write dy dx. So the derivative of x is 1. Derivative of y cubed is 3y squared, dy dx. Derivative of 2y is 2, dy dx. And derivative of negative 10 is just 0. I can then isolate my dy dx. So dy dx, 3y squared plus 2. So then dy dx, 1 divided by 3y squared plus 2. And that is the derivative of my inverse function. Okay, so let's look at example 28. Example 28 has multiple parts. So the first thing was to find, part A says to find f of 1. So f of 1 is equal to 2 times 1 to the 5th plus 1 cubed plus 1. So f of 1 is equal to 4. Part B, since f of 1 is equal to 4, then f inverse of 4 is equal to 1. So I can flip my x and y, and that would give me the value at the inverse. So f inverse of negative 4 is equal to 1. Okay, because if I had a coordinate point 1, 4, then on the inverse I'd have a coordinate point of 4, 1. Okay, so then C, because remember with inverse functions, before I go on to C, with inverse functions you flip your x's and your y. In an equation you flip your x's and your y and you resolve for y. In a table of values, if I have my original function in a table of values, I just flip the coordinate points of x and y and I can resketch what my inverse function actually looks like. Okay, so then I need to find f prime, or f, the derivative of the inverse. So I have x is equal to 2y to the 5th plus y cubed plus 1. Take the derivative implicitly. 1 is equal to 10y to the 4th plus 3y squared plus 0. And this is all dy dx next to it. Isolate dy dx. So 10y to the 4th plus 3y squared. Divide both sides by that parentheses, so dy dx is 1 divided by 10y to the 4th plus 3y squared. I want f inverse derivative at 4. since 4, 1 is a coordinate on f inverse of x, then when I want f inverse derivative at 4, I'm plugging this y value in. So 10 times 1 to the 4th plus 3 times 1 squared. So f inverse prime of 4 is equal to 1 over 13. Okay? So to do this, I had to actually find a and b before I could evaluate that inverse at 4. Okay? So example 29, find the second derivative, so y double prime. So first let's find y prime. Second, which is cosine of x times the derivative of the first, plus the first times the derivative of the second. So y prime is cosine of x minus x sine of x. Take the derivative one more time, so y double prime. Cosine derivative is negative sine. Minus a product rule, so sine of x times the derivative of x, which is 1, plus x times the derivative of sine, which is cosine. So y double prime, negative sine of x minus sine of x minus x cosine of x. So y double prime is negative 2 sine of x minus x cosine of x. Okay, so the last one is regarding L'Hopital's rule. L'Hopital's rule is a evaluation of a limit. But in order to evaluate the limit, you actually have to take the derivative, which is why this is in this particular lesson versus a different lesson where all the limits were. So L'Hopital's rule is designed to find this limit when nothing else works. You get 0 over 0, infinity over 0, 0 over infinity, or infinity over infinity. And what you do is you take the limit as the derivative of the numerator divided by the derivative of the denominator. So this is not quotient rule. Derivative of the numerator divided by derivative of the denominator. And if that's the case, you take this derivative as many times as until you can plug in this value of a so that you don't get one of these 4 situations. So when I look at example 30, limit as x approaches 0, derivative of 1 is 0, minus the derivative of cosine, which is negative sine of x, divided by the derivative of x squared, which is 2x. I still can't plug in my, my 0 in for my x's, because I get limit as x approaches 0 of sine of x over 2x. I then take my derivative one more time. So limit as x approaches 0. Derivative of sine by itself is cosine. And derivative of 2x is just 2. Now that I don't have 0 in the denominator, I can go ahead and plug in my 0 in for my x. So cosine of 0 divided by 2, and the cosine of 0 is 1. So this limit originally here is equal to 1/2. And that is it for this lesson.